This is a project on roller coaster simulation, modeling energy conservation, and motion on a custom track. The objective of this project is to model our motion of the roller coaster, specifically how potential energy is converted into kinetic energy and vice versa. The motivation is to simulate the behavior of a roller coaster to understand fundamental physics concepts in the real world. And the purpose is to explore how potential and kinetic energy interact with roller coaster system as the roller coaster moves along the track. And we can visualize these changes and confirm the energy principle of conservation, which states that total energy in a closed system remains constant. So the basic physics concepts are kinetic energy with its formula that's seen here, potential energy with its formula is seen, and the total energy in a closed system is the sum of kinetic energy and potential energies. And in the ideal frictionless environment, this is total remains constant throughout the roller coaster's motion, and gravity acts as the driving force that accelerates the roller coaster downwards and converts potential energy into kinetic energy as the coaster descends along the track. So the track has initial descent, where the roller coaster starts from the highest point and descends to the potential energy converted to kinetic energy, increasing speed. The flat section where it levels out, the ascending slope where the roller coaster climbs, converts kinetic energy back into potential energy, causing it to slow down, and another constant height, as we can see in the graph here. In relation, the total energy of the roller coaster remains constant throughout its motion. The total energy is determined by the potential energy at the initial height, as you can see the equation here. And since the roller coaster starts at rest, we have another equation here. And energy transformation is seen by potential energy, kinetic energy, and total energy, which remains constant. This is my code with key snippets. So on track height, we have this code, which defines the track shape, which affects energy transformations. For total energy, we have this code, which calculates the total energy at the start based entirely on potential energy. For velocity, we have a velocity uh, function which computes the roller coaster velocity using energy conservation principles, and the track height function shapes the track and affects the energy calculations. The energy calculation functions ensure accurate modeling of energy transmissions, and the velocity function links energy changes to the roller coaster motion. Simulation results. The graph illustrates the track's four sections: initial descent, flat section, ascending slope, and constant height. The track profile demonstrates how changes in height impact the roller coaster's energy transmissions and speed, validating the principles of energy conservation. Here's the other results with kinetic energy, potential energy, and total energy. So we can see the continuous transformation between potential energy and kinetic energy highlights the dynamic exchange between motion and height while maintaining total constant energy. How would roller coaster motion and energy profiles change if frictional forces were added to the track? The energy would no longer be conserved, and as some of the mechanical energy would be lost to heat function. What would happen if initial height of the roller coaster increased beyond the original 50 meters? The total energy of the system would increase. And what would happen if a loop is added to the track, requiring the roller coaster to maintain enough speed to complete it? In this case, the roller coaster must retain sufficient kinetic energy at the base of the loop to counteract gravity and centripetal force of the loop's peak. And if the initial height is insufficient, the roller coaster may not complete the loop and could stall. So I gained a deeper understanding of energy transmission and conservation. Additionally, the project improved my skills on Python programming, numerical modeling, and data visualization. For future work, I plan to incorporate friction and air resistance for greater realism, design more complex tracks with loops or variable slopes, and study passenger forces and forces upon the passenger, such as g forces, for enhanced ride analysis. Thank you.